Hello, everyone. Lights are a little bright. I'm Akshay Shah. I'm a senior software development manager at Oracle in the database virtual OS team. And I'm going to be talking about how we integrated SPDK with the Oracle RDBMS talk. In addition, there's also a co-speaker, Bang, who's going to be covering a few aspects of the talk as well. So just to quickly go over the safe harbor statement. A lot of this is sort of future work. It's not available in an Oracle release. I'm required to mention this in most public forums. So let's get that out of the way and move on to the actual agenda of the talk. So we're going to be talking about SPDK, some of the benefits that it provides, what were the challenges that we faced while trying to integrate it with our Oracle RDBMS stack, how we solve those challenges. We'll go over the Bang will go over the Oracle dispatcher, then the memory model, and then some future work there. So I'm not going to really cover the SPDK architecture. There were a few talks early on which sort of gave you an introduction, roadmap, and so on. So let's quickly move on to what are the benefits that SPDK provides that are really relevant for the Oracle database. So one of the most important aspects for the database is to have low latency when we're doing our IOs. And this is something that SPDK enables and helps us achieve. So in a sense, it's enabling us to scale our database application with really a scalable storage tier. As some of you have seen the performance numbers, we can achieve millions of IOPS from an application to these really fast NVMe drives. One important point to cover here is from the database perspective, we're really interested in low latency. So while we have some local devices as well as remote devices that we can access using NVMe over fabrics, we make a distinction in what's local versus remote, because local gives us even lower latency than remote devices. And a lot of the talk will be focused on that point as well. And then all of this sort of fits in the Oracle I/O model, which is we want to do direct asynchronous I/O, zero copy wherever possible, and using as little CPU as possible as well. So moving on, what were some of the challenges that we faced as part of this? So as was covered in one of the talks earlier today, some of these NVMe SSDs have a limit on the number of hardware queues that are exposed, especially when you're accessing these directly as local devices as opposed to using NVMe over fabric. The Oracle database usually has a lot of processes. Most databases on average have hundreds of processes, and these are what we consider small deployments. Larger deployments have thousands of processes and a set of nodes running a rack cluster. So whenever we are trying to access the NVMe SSDs with these many number of processes, we run out of the hardware queues very quickly. So this was a significant challenge that we faced, and Bang will go into a lot of detail as to how the Oracle dispatcher helps us solve this problem. The other significant challenge that we had was we have a very sophisticated existing memory model, and I'll go into more detail on what that memory model looks like. But the key point here is that memory model sort of conflicts with how DPDK works and its memory model. In the standard default implementation, DPDK is doing a lot of tasks that abstracts out some of the hardware specific and the memory specific things. That doesn't quite work in the Oracle RDBMS deployment. So that was a challenge that we also had to solve as part of the integration that we had to do for SPDK with the Oracle database. So moving on, Bang will come up and talk about the Oracle dispatcher, which helped us solve the hardware queue limit.
Good afternoon, everyone. My name is Bang Nguyen. I'm here to talk about the Oracle Dispatcher. So as Akshay has mentioned, one of the big challenge we had was the hardware limitation on IOQ. For SPDK to be a viable solution for Oracle, it needs to scale up. And originally we had a simple model. For every process, it go through, basically for every process, it has to first discover the controller, and then it has to allocate the IOQ. We later found out that, depends on whether the controller is local or remote. SPDK will allocate either a physical IOQ or a virtual. For virtual IOQ, the number is pretty high, so we don't have to deal with it. But for local, for physical IOQ, we know that the NVA device usually comes with a limited number of queues. And if every process has to allocate a physical IOQ, it's going to limit our scalability. One solution was to come up with some kind of a scheme to share the IOQ. And we came up with, basically we have come up with some kind of proxy. In our case, it's dispatcher. So the dispatcher here, basically you look at the stack, there's two paths to SPDK. If it's a local, remote I/O, we directly deal with SPDK. If it's a local I/O, we go through the dispatcher, and the dispatcher is the one who allocates all these physical IOQs, and it's shared across the clients. Obviously, we solved that problem. Now we can scale up to more than the number of physical IOQ, because all the client can go through the dispatcher, and the dispatcher will do the allocation. But adding a dispatcher basically is an overhead, right? Because now everything's funneled through the same channel. So, go through, this is basically our design, and our goal was to streamline the dispatcher to minimize all the overhead, because obviously you add more overhead if you add an extra layer between the I/O or I/O stack and SPDK. So we came, this is our design. Basically, the idea was to utilize all the available cores and adding the number of processes that the dispatcher can utilize. So you look at this design. This is our dispatcher model is based on a multi-core, multi-process design. The dispatcher basically is a component, and it can run with multiple slaves. Every slave has multiple request queue, right? And the client will send requests to submit requests to the dispatcher request queue. The dispatcher slave will pick that up and submit it to SPDK. And this is on the client side. So the way we do it is, every client, we statically bind to a particular core. Because the idea was to distribute the workload across the core. That's how we scale. And you have to distribute across the core and also distribute across the slave. So the dispatcher, the client has to bind to a specific core, to spread them out. And you look at, as far as the dispatcher is concerned, you look at the slave, it has to reduce the overhead. It has to run in a dedicated core, right? And the client can share the core across across the node. And if you, so basically the first thing is that we bind the client to the dispatcher queue. And then the client will send a request to that queue, whatever queue that is bound to. The dispatcher will pick up the request and then submit it to SPDK. Okay, because the dispatcher is an added overhead, we have to streamline it and optimize it so it's to minimize the overhead. You look at this diagram. Every client has its own completion queue, right? And it submit requests directly to the dispatcher slave. The dispatcher slave picked up the request and submitted to SPDK. SPDK, and then it will go through and pull for the completion. For every completion, it will queue up to the respective completion queue, the client completion queue. The client will pick up the completion and process that completion. So this is the general flow, how we design our dispatcher to minimize the overhead. Any question? That's pretty much the slides for our dispatcher. Yes.
Could you give us a sense of 1 second? Hi.
Hi.
I'm trying to get a sense of how many cores are we talking about here, because you said your initial constraint was the limited number of queues available.
Could you say it louder? Can you?
How many cores are you typically talking about here? And I ask this because you said you are constrained by the number of queue pairs available.
I didn't hear that. Sorry.
I think the question was how many cores are the dispatchers themselves using, because the hardware queue limit.
Yeah, since you mentioned there is a hardware queue limit is coming in as a constraint for your application.
Right.
I'm trying to get a sense of that number. Are we talking 32?
Well, in our system that we're using right now is 32, around roughly 32.
Okay.
Yeah,
Right.
so it's configurable. The number of dispatchers is configurable. Depending on the system size, we can scale that number up or down.
Right.
So
of course, staying under the hardware queue limit.
Okay, thanks.
Yeah.
So I have a question is, the slave, so is a separate process from the client, right? So
Yeah.
what's the communication channel between the client and the slave? How do you submit the I/O request to the slave?
Yeah, the communication basically is the lock-free rings. It just queued up the request to the request queue, and it basically is a lock-free key ring, and it queued it up, and the dispatcher slave will pick it up and process them.
Hey Bang, we're gonna hold off questions till the end, because I know you guys have some more slides. So let's go through the rest of the slides, and we'll have time for more questions
Okay.
at the end.
Yeah, that
Thanks.
sounds fine.
Okay.
So moving on. So I think just to address the question that was asked, once I cover some of the memory model, some of the things will be a little clearer as to how this works in the Oracle ecosystem. So let's quickly go over what DPDK provides us today. So SPDK by default uses DPDK as the runtime environment, and it leverages it for doing some of the huge page management, also allocating the memory. So I'm distinguishing private and shared memory, and it'll become a little clearer as we go over the next few slides. And also it provides other functionality when you're running as a primary secondary model with a target. And additionally, there's like PCI enumeration, address translation that it provides. So let's sort of look at what Oracle's existing memory model looks like. So we have three major components in Oracle's memory model. There is something called PGA, which is private global area. This piece of memory is specific to the process. It's not shared between the other processes that are running and part of the same instance. And there are, in addition to using that memory for data structures, computation, and so on, there are also database workloads where we use PGA memory to do IOs. The next big piece of memory is SGA, which is a shared global area. This is usually the largest component of memory in a running Oracle instance. This is shared between all the processes that are running. So anytime there is a process spawning, there are a set of steps that happen, and one of the steps is to map the SGA address range into that new process that's coming up or connecting to the database. In addition to the SGA, we have something called the MGA. MGA is a managed global area. The main distinction between SGA and MGA is while this can also be shared between processes, this is more access controlled. So only select processes are mapping and accessing the MGA. It's identified by a name, and then you have a key to sort of attach and detach. And segments can be added and deleted based on the memory requirements of what's going on. So these are sort of the three memory models that we have. And we can see that DPDK doesn't quite work the same way. And that's why we had to sort of come up and do our own ENV or an environment abstraction layer. So just a quick summary on what an EAL provides today. And DPDK, as I mentioned earlier, is the default that SPDK uses. So it sort of abstracts out some of the hardware specifics, like accessing PCI devices and so on, how the memory management works underneath, huge pages, address translation, and all of these functionality would need to be replicated in our ENV implementation as well. The other thing that it does is sort of the core management and affinity handling and so on. So that's sort of what DPDK was providing, and that was sort of the minimum requirements of what we had to build in ORAENV, which is sort of our equivalent for it. So I'm going to cover a couple of the important components of this. So one is how do we do the memory management, and how do we integrate it with the three pools that we described. So there's the SGA and MGA pool, and I'll talk about how our heap allocator looks like as well. We also need to do some of the other functionality that DPDK provides just to get it to work and for completeness. And then the other point I'll cover is I mentioned the SGA and MGA can be relatively large, and to do low latency I/O with lower CPU usage, we want to do RDMA wherever possible. So there are some optimizations that we've already made in the Oracle database for our RDMA, and how do we enable those with this model. So this is sort of a picture of the three pools that I described. So there is the SGA sort of, which is in the center, and the various processes are accessing it. Buffer cache is sort of an obvious component of the database that you can see in there. And also the question that was asked about how do you communicate with the dispatcher. So you can allocate memory from SGA, which is mapped in both the dispatcher and all the slaves. So a lot of the communication is enabled by SGA. And then each process sort of has its own private area that's listed in the PGA component. So how does this all work? So we have our own heap allocator. The space is fragmented into various heaps. Each heap is either a PGA heap or an SGA heap, and it's an extent base. So the slave, when it's trying to allocate a memory, would pick a heap based on whether it's trying to allocate the memory from SGA or PGA, and then the corresponding heap is used to allocate the memory. The heap itself consists of chunks and fragments of different sizes, and there are various optimizations in there to prevent fragmentation and optimize the allocations and so on that are sort of beyond the scope of this, but this gives a high-level overview of how the heap allocator looks like. Then the second part that I mentioned was to enable zero-copy data transfer. So whenever we have such big pieces of memory and we want to do RDMA, and you have thousands of processes, a big scalability bottleneck is how do you register this memory in every process that's running as part of the instance. So to solve that and to prevent the overhead and the scalability challenges with it, what we've done is use shared protection domains, and it basically helps limit the scalability challenge. So what it does is you have a process, actually, let me go to the next slide and then I'll come back. So this is what it looks like. So you have a first process which allocates a shared protection domain and then registers the memory using that protection domain in that process. And then all other processes that are attached to the same SGA or MGA regions can map and attach to the memory, and then they can use the same protection domain for their registrations and so on. So with this model that we have, we can enable zero-copy data transfer for SGA and MGA memory, which is sort of pre-registered as part of our database startup when we have background processes that do those tasks. So going back over some of the benefits that shared PD gives you. So the first obvious benefit is the scalability. So with a single process doing the registration, we can share that across a set of processes for SGA and MGA memory. The other advantage is it improves, HCAs have their own caches similar to TLBs. So it improves the cache performance in SGAs whenever you're doing lookups for various keys and so on. You can have read-write accesses. As long as a single process is attached, the PD stays valid. So while the database is up and not shutting down or something, all that memory is still registered and the keys and everything is valid. And effectively, since we are sharing this, the lookup service can be really quick. So this is another picture of how the same thing can be enabled for SGA and MGA. As you can see over here, all the processes are mapped to the SGA. So if you have a protection domain for it, those keys are used by all the processes, and then P1 and P3 over here are attached to an MGA a piece of memory, and only they would have access to that memory and the protection domain key for it. So moving on to some of the future work that we're looking into. So part of the database deployment model is on a single host, you can have more than one database running. And we usually try to do some kind of quality of service from the storage standpoint for the different databases. We also have a model where you're running within a single database different kinds of workloads. So we would like to provide the ability to do some sort of rate limiting, both for IOPS as well as throughput for different databases and the various workloads running within the database. The workload could be a standalone database, or we also support a container model where within a single container DB, you're running various pluggable databases or various tenants. So we would also potentially want to provide the ability to do QoS at that level. Within a single DB, you can have higher priority and lower priority tasks. If you're doing a database backup, that's usually high volume, but low priority. You don't want that to impact other higher priority tasks such as a log writer and so on. So we would want some kind of an ability to prioritize these latency sensitive IOs and prevent high volume IOs from impacting the latency for some of those. The next aspect I'll cover is security management. In both the single host multiple database model as well as in a container and multiple tenant model, we want to enforce some sort of access control and security. The devices today in the subsystem are visible to the host using the NQN. There's no sort of implementation for authentication or for even visibility to devices that's enabled. So that's something we would like to do, sort of tie it with the connection model. So authentication and connection sort of go together, and then potentially using the same connection model, you can associate it with a QoS policy as well, tying everything down at a namespace level. So that's sort of the roadmap that we're looking at to do access control for namespaces using connection-based authentication and potentially QoS as well. The other aspect, which is sort of outside of SPDK itself, is potentially using encryption of data that's going to remote targets over the wire. So we'll be looking into IPsec as well to encrypt data that goes over the wire. The third part of future work that I wanted to cover is the transport. So a lot of the testing that we're doing currently is using accessing these NVMe devices using RDMA, both local and local are over PCIe, but the remote devices are through RDMA. TCP is obviously a lot more standardized and commonly available in data centers, including all our Oracle cloud data centers. So that would be something that's really interesting and on our roadmap. The NVMe working group is working on it already. So we're hoping and eagerly awaiting the specification part of it and the SPDK TCP support as well. So that sort of covers what we had. So just to reiterate and conclude, so SPDK basically enables really low latency IO performance for the Oracle database. As Bang explained, we've implemented the Oracle dispatcher to make sure we can access local devices with really low latency as possible. The ORAENV, which is our environment abstraction layer, sort of does some of the DPDK functionality, but also lets us integrate with our memory model and enables enables the memory management, the address translation, and so on. And also it enables us to use our shared protection domain approach to do RDMA for both local as well as remote IOs. So yeah, so that's basically what we had to cover. So we can open it up for questions. In addition to me and Bang, we also have Zara and Avnish who are working on the project. So whether you have questions now or if you want to find us later during the day or tomorrow, we should be around to help answer questions.
Question over here.
And Bang, do you want to come up as well?
Hello. Hi there. So I have a question about your Oracle dispatcher. It seems like it's just adding extra queues, right? So is not that possible to push that functionality in SPDK itself? Like, can SPDK be extended to provide more queues instead? It's both SPDK
do you
and
want
Oracle.
us to answer it or the SPDK first?
Yeah, both of you can comment on it, I guess.
Yeah, so I think there's some work that we've done on the vhost side of things to be able to provide this type of dispatching functionality. And so yeah, I think there's an opportunity to take some of the work something similar to what Oracle's done and move that into SPDK in the future. There's been a few things for supporting vhost for other user processes that has needed some work. There's been some things in the most recent version of DPDK that are going to make that a lot easier, and so I think that's something that we could definitely add more general support for in upstream SPDK in the future.
Yeah, otherwise everybody is going to come up with their own dispatcher.
Yep, exactly, yeah.
Hi. What kind of performance improvement did you see with integrating with SPDK? Did you have an existing non-SPDK approach to accessing these devices, and how much improvement did you see?
Well, we don't have official number yet, but very preliminary. We were able to, using AKIO with five client process, we were able to get up to over 1 million IOPS, and basically maxed out the device. So, so that's a good number. But we're still developing it, and we'll get the official number later. But so far, it's looking good.
What about latency? Any latency numbers? Latency.
Well, it's relatively comparing with PERP, because that's the benchmark, that's the base we're trying to compare with, and it's relatively the same. So the overhead based on our design is very low, and we were able to scale up to hundreds of processes. I mean, that's very important for Oracle, because if we cannot scale, then it's not a viable solution. Our goal is to get up to, say, in the thousands process, because that's a typical deployment. So that is still work in progress. But so far, so good.
Thanks.
Okay. With that, I think we're going to move on to the next presentation. Thank you.